Okay, so thank you very much, Ugo, and of course also thanks, James. Well, of course, thanks for organizing these very nice seminars and for inviting me. It's always a pleasure to have the possibility to give a talk. As you said, and as the title of the talk says, I'd like to discuss with you some very recent results obtained about ground states for nonlinear Schrödinger equations. Okay, so I mean, NLS equation has been studied all along the decades. So let me just start with the problem, which is, I believe, a very well-known problem by everybody. This is the equation we will consider. You see, we got a nonlinear Schrödinger equation in the sense that we got a pure power nonlinearity term on the right-hand side. Here, the exponent p of the nonlinearity will always be Sobolev subcritical. Okay, so it will range between 2 and 2 star, where 2 star is the critical exponent for the Sobolev embedding. That, of course, depends on the dimension of the space. You see that we got also a real parameter in the equation, okay, this lambda here, which multiplies the linear term u. And we will consider this kind of problem on a general, possibly unbounded open subset of Rn, okay? Endowing the boundary of the domain omega with the homogeneous Dirichlet boundary condition, okay? So it is a very well-known problem. It has been studied a lot. So let me just, to get to the question we're interested in today, let me just start with a very, very quick review of some of well-known facts about this equation. The first thing is that this is a stationary problem. And as any stationary problem, if you solve the stationary problem, you can obtain a corresponding solution for the associated time-dependent problem. Okay, so if you got a solution u of problem 1, then you have a standing wave in this form for the time-dependent NLS equation, which is, of course, a complex equation. There's I here, and the homogeneous Dirichlet boundary condition remains. And as it's well known, this equation, this time-dependent problem, admits conserved quantities. In particular, we recall that the energy is a conserved quantity, where the energy is given by kinetic term, which is the square of the gradient of the solution psi, and the pure power nonlinearity term with the minus. And also the mass is another conserved quantity. In this case, the mass is just the square of the L2 norm of the solution. Now, of course, this kind of conservation holds for every solution psi of the time-dependent problem. But since we were starting with the stationary one, if you take psi to be a standing wave, then the energy and the mass still are conserved, but the integrals in the expression just involve the part of the solution u, which is a solution of the stationary problem. This is an integral in u, an integral in u, an integral in u. Okay, so only in the spatial variable dx. And since we got these conserved quantities, we can rely on them to try to tackle the problem, the stationary problem, from a variational point of view, okay? And again, this is very well known. There are at least 2 main different strategies that have been exploited all along the decades to tackle this problem, okay? The first one, we can call it the action approach, is to consider the so-called action functional, which is this guy here, this j lambda here. Note that there is a subscript lambda in the definition of j, because here lambda, the precise value of the parameter lambda, appears in the definition of the functional, and therefore here we are fixing the value of lambda at the beginning, okay? And one can try to find solution of the stationary problem, the NLS problem, looking for critical points of this action functional, constrained to the so-called Niari manifold, which is just the manifold of function u fulfilling the boundary condition that satisfies j prime of u times u equal to 0. This is general. In our situation, given the definition of j, this just amounts to this second line here, okay? Why this is a good idea? Well, because it is well known that the Niari manifold in this setting is a natural constraint, in the sense that critical points of j lambda on the Niari manifold are actually unconstrained critical points of j. And this means that they solve the original NLS stationary problem we were considering. Okay, there is no further Lagrange multiplier arising associated to the Niari manifold. So like this, we can find solution of our original problem. As I said at the beginning, this kind of solution will be, say, solution with given frequency. In this kind of problem, the parameter lambda, the value of lambda, can be interpreted as the frequency of the solution you find. And since we're fixing lambda at the beginning, like in this way, we find solution with a given frequency. But of course, this is the only thing you know a priori about the solution. You do not know anything else. In particular, you do not know anything about the mass of the solution you find following this approach, okay? At least not a priori. If for some reason you're interested in solution with a given mass, then you can try to exploit another approach, which is the looking for critical points of the energy function, which is the one we've already introduced at the beginning, this one here. But now you look for critical points in the mass-constrained space, which is the space of function, the square of the L2 norm of which is set equal to a given parameter, okay? Let me just say one thing here, okay? You see there is this factor 1/2 in the definition of the mass-constrained space. Now, it is completely inessential, okay? It is there just for numerological purposes, in the sense that if you take this 1/2 here, then some formulas in our results simplifies, okay? Appears in a more, say, neat formulation. But of course, if you don't like it, you can drop it. Here, you just take the square of the L2 norm of U to be equal to mu. And then at the end, all our results remains true. They are the same with just minor differences. There are some powers of 2 that appears here and there in some explicit formula, okay? But it is completely inessential. The other important thing is that now we are fixing a priori the mass of the solution. So following this approach, we do not know anything a priori about the frequency of the solution we find, okay? Now lambda arises as a Lagrange multiplier associated to the mass constraint, but you do not know anything about it, about its precise value a priori, okay? Well, these are two different approaches. Of course, you're free to look for the kind of critical points you prefer, but it makes pretty sense to start with global minimizers, okay? And from now on, we will refer to global minimizer of any of the two functional as to ground states. So we got two different approaches. We got two different notions of ground states. On the one hand, I can consider global minimizer of the action on the Niari manifold, and I will call them action ground state. And the level of this, the action level of this guy, will be called the action ground state level. It will be denoted by J. Of course, it is just a function of lambda, okay? Calligraphic J of lambda. And similarly, you can take the energy approach, look for global minimizer of the energy in the mass constraint space. They will be called energy ground state. And the energy of these ground states, which is of course just a function of the mass, will be called the energy ground state level. It will be denoted by calligraphic E of mu, okay? These two are one-dimensional function, okay, on the parameter lambda and mu. Okay, well, of course, these kind of approaches have been widely exploited all along the history. The key point is that both of them provides you with solution to kind of the same problem, in the sense that the critical points both solve this kind of NLS equation. From the historical point of view, action ground states came first. At least we can trace them back to the beginning of the 80s, even the end of the 70s of the last century. There are a lot of people that have been working on this all along the year. Let me just restrain myself here to recall the seminal paper by Berestiki and Lyons. Whereas the mass-constrained approach seems to be a bit more recent, okay? Maybe the starting paper, at least in the context of nonlinear analysis, is the one by Jean-Jean in 1997. But after that, a lot of people have been working in this kind of problem, in the energy approach, in the last few decades. And here you see an incomplete, very incomplete list of some of them, okay? So both the approaches have been exploited. Of course, both the approaches are intertwined, in the sense that if you take a critical point of the energy in the mass constraint space, this will also be a critical point of the action in a suitable Niari manifold, and vice versa, okay? So, I mean, it seems pretty natural to wonder if there's any relation between the two of them, okay? In the sense that, what can we say about the solution we find with one approach and about the solution we find with the other approach? It seems that this kind of interplay has not been thoroughly investigated yet, okay? In particular, I mean, even from this very, very, say, fast introduction, there are some questions that I believe naturally pops to your mind. For instance, one can wonder, I mean, I believe this is maybe the most natural question. What about ground states? Are energy ground states also action ground states or not? Or vice versa? That is to say, we got two different approaches to tackle existence problem for the same equation. But are they really different? Do they really provide us different solution, or in the end, we're just looking at the same solution and we're reaching it following two different ways? Quite surprisingly, it seems that there are no available information about this kind of question in the literature. And so these are quite kind of the problem we're interested in today, okay? So to get to that, the point is, let's investigate the interplay between the approaches. Before getting to the interplay, let me just very quickly recall some properties of the two problems independently, and in particular of the two energy and action levels as one-dimensional function, okay? Because they will be important in the form. On the one hand, let's start with the energy. If you look at the ground state energy level, I believe it is very well known that there is a critical exponent, the so-called L2 critical exponent for the problem, which depends on the dimension. It is P equal to 2 plus 4 over n. When you look at power that are L2 subcritical, so below the critical exponent, the energy is always well-defined for every mass, and it is always a concave function on 0 plus infinity. If you go at the critical exponent, there is a threshold on the value of the mass. There is a mass mu n greater than 0, such that for masses smaller than this one, the energy is finite, and it still is a concave function. But if you go to larger masses, then you end up with the energy being equal to minus infinity, okay? So you got a sharp transition between finiteness and infinity of your energy, ground state energy level. If you go to L2 supercritical power, then the energy is always minus infinity. That means that there is no energy ground state for any value of the mass, okay? As I was saying, I believe this is almost well known by everybody. Let me just say that here, there is no role of the domain omega. In particular, you see here we got a threshold mu n, but this threshold is insensitive to omega. It is always the same value for every open subset of R. Okay? It is related to some Gallardo-Nirenberg inequalities, but the key point is that omega here doesn't play any role in giving this property. The role of the domain starts to be important if you look at similar properties of the action ground state level. And in particular, to recall some known properties of the action ground state level, it is important to introduce the bottom of the spectrum of the Dirichlet Laplacian, which is just the infimum of the Rayleigh quotient. You see, it will be denoted by lambda omega to stress the fact that this depends, it is a number that depends on omega. And given this, the thing we can say from the very beginning about the action ground state are the following ones. First thing, the action ground state, level J lambda is always finite for every power P and for every value of lambda. It is strictly greater than 0, strictly positive, when lambda is larger than minus lambda omega, and it is always equal to 0 when lambda is smaller than minus lambda. J also is an increasing function, always on R, and it is continuous. In full generality, at the moment, we're only able to say that it is continuous on R, except at most the point lambda equal to minus lambda omega. Okay, the fact whether or not J is always a continuous function on the whole R seems to be an open I gotta say, quite tough problem, at least for me. Okay, and then of course we got a characterization of the asymptotic behavior of J. In particular, J is superlinear at infinity when P is L2 subcritical. It is asymptotically linear when you're looking at the L2 critical exponent, and the asymptotic slope is exactly the threshold mu n we've been seeing before. And then it is sublinear when you're looking at the problem at L2 supercritical. Okay. Again, nothing very surprising, nothing very new up to now. We've been seeing by now some list of properties of the two problems independently. So let's now try to understand if there is a relation between the two. And to warm up in this, trying to build some heuristic for the general situation, let me start showing you the unique situation where everything is already well known, which is the case of omega equal to the whole space Rn. In Rn, the problem is well known since decades. Everything is explicit, okay, almost explicit. In particular, if you look at the problem, say, for the sake of simplicity, for L2 subcritical power, then the situation is this one. Both the energy and the action, ground state level, are power function of mu and lambda respectively, okay? The exponents can be computed explicitly. It is not important to remember these explicit values of the exponents. The important thing to note is that there is this relation between the exponents. There is 1 over alpha plus 1 over beta is equal to 1. If you want, alpha and beta are conjugate, okay? I mean, this is a pretty strong relation between the two energy, ground state and energy, ground state levels. So one may start to wonder whether or not this is a coincidence, in the sense that maybe this is something that happens only in the very special case of Rn, or maybe this is something that gives us some idea about what may happen in a more general situation for a more general omega, okay? Well, let's try to immediately see that generalizing, however, from Rn to a general omega, it is not a very straightforward procedure, because let's now try to think of another very well-known situation, a problem that has been studied a lot all along the decades, which is not omega equal to Rn, but omega a given bounded open subset of Rn. Well, now we are already losing some of the information we have on Rn. In particular, we do know, because this is already true, and we said it before in our, say, list of well-known properties of the energy, that the energy is always a concave function. This is always true, okay? But we didn't say anything about the possible convexity of J. So in Rn, J is a perfect power. In particular, it is convex. Of course, we're talking of the L2 subcritical case. But what about omega bounded? Do we know a priori that J is convex? We do not know it a priori. So is it J convex or not? Up to now, we do not know. You see, it is quite of an interesting question, in particular, based on the fact that the energy is always concave, okay? So you see that even moving from omega equal to Rn to omega a bounded subset of Rn, there are many more questions that are coming. We do not know anything very precise and general about the relation between the ground state levels, if there's any relation. We do not know anything about the relation between the ground states, the minimizers. We do not know if J is convex, even though E is concave. And be careful, this is not just a silly, say, theoretical question. It is also important because since we know that the energy is concave, we immediately know that it is differentiable up to at most countable sets. But if we do not know, as it is, that J is convex, we do not even know anything about its differentiability. Okay, so we do not know anything about regularity of J. we do not even know if there is some relation, not only at the level of global minimizer, but also at the one of local ones. And of course, we do expect, at least if the problem is not trivial, we do expect the domain and the nonlinearity to play some role. Okay, so we do wonder how this kind of question do depend on the domain, on omega and on p, and on the parameter of the problem. Okay, so these are quite some of the questions I'd like to try to answer in the remaining part of the talk. Okay. Before providing you with our results, let me just say once more that very, very, very little is known in general for this kind of question. And in particular, in all the situations where something is known, almost every time it is based on the fact that we already have uniqueness of the positive solution of the equation. This is the case of Rn, this is the case of the ball, for instance. But the problem is that, as I believe you know even better than me, way better than me, uniqueness in this kind of problem is a very, very challenging issue. In a lot of situations, it is even false. Okay. So in particular, this leaves us with Rn, as we already saw. And in particular in Rn, in the L2 subcritical case, given the fact that the solution is always unique and they are the soliton, we already know that energy ground states are also action ground states, and vice versa in the L2 subcritical case. But this is because we got just a unique solution. The very same thing is known on the ball, but again, because we have a unique solution, a unique positive solution. If you get rid of the ball and of Rn, nothing is known in this direction. More than this, even if you look at Rn and the ball, there are some instances that are somewhat suggesting us that a very, say, strong relation, such as the one, say, for instance, energy ground states and actual ground states are always the same thing. Even if we restrict our attention to the well-known case of Rn, we immediately see that this cannot be true, at least not in general. Because if you look at Rn, the problem with a supercritical, L2 supercritical power, so P larger than 2 plus 4 over n, the solution is unique. It is the soliton. It is an action ground state, but it is not an energy ground state. This is trivial because the energy is unbounded from below. There is no energy ground state. More than this, it is not even a local minimizer of the energy in the mass constraint space. Okay, and the very same thing is true also on the ball. This is, say, a straightforward consequence of some of the results given by Norris, Tavares, and Berzini in 2014, in combination with some results by Fukuizumi and collaborators. Okay, so you see, if you look at the last point, we see that even on Rn, action ground state cannot always be energy ground state. Okay. So the situation seems to be not that straightforward, even in the case of Rn. Now let's see what we can say in full generality for a general open subset of Rn. Well, first result we have is about the relation between the ground state levels, between calligraphic E and calligraphic J. Recall that, as I said before, on Rn, the two functions are perfect powers, and the relation between the exponents is this one, their conjugate. This is not a coincidence. Of course, in full generality, we do not even know that calligraphic E and calligraphic J are perfect powers, okay? Because we do not have the invariance by dilations, okay? So they are general functions. We're not able to say they are perfect power. But the thing we can always say is that minus calligraphic E, minus the energy level, is the Legendre-Fenchel transform of calligraphic J, of the action level. Whereby Legendre transform, we mean this by definition, the supremum over lambda in R of lambda mu minus J lambda, okay? Now, this is interesting. Why it is interesting? First thing, because it is extremely general. The validity of this equality, minus E equal to J star, does not depend on omega. It does not depend on the fact that J and E are actually attained. That is, on the fact that ground states really exist, okay? And it doesn't even depend on the fact that the energy is finite or not. Remember, J is always finite, but calligraphic E may be equal to minus infinity, okay? For instance, in the L2 supercritical case. Even in that situation, this equality is true, okay? In that situation is even, say, trivial, okay? But it remains true. And why is this somewhat interesting in connection with the situation on Rn? Oh, because if you take a perfect power, say you take this J lambda equal to lambda to the power beta, you use the definition of Legendre transform and you compute the Legendre transform of this function here, you end up with another perfect power, and the exponent in the transform is exactly given by the previous one through this relation here. So if you want, in some sense, what we have on Rn is of course stronger than what we have in the general situation, but what remains in a general domain of this strong conjugacy between alpha and beta is this relation about differential transform. And this is interesting also because once you got this identity, you immediately have also the following result about ground states, about the minimizers. You can say that any energy ground state, which of course, if you have a ground state, an energy ground state, then that is a function. It has its own frequency. You can compute it. Then that function is also an action ground state in the Niari manifold corresponding to that frequency. And more than this, all other action ground states at that frequency will have the same mass of your original energy ground state. And they will all be, of course, also energy ground states in the mass constrained space. So what we are trying to say here is the following fact. First thing, we are starting answering to one of our original questions. Are energy ground states also action ground states? The answer is yes, in full generality. But more than this, we are identifying a sort of rigidity of the variational framework with respect to energy ground state, in the sense that whenever you got one energy ground state, the problem for the action at the frequency of that ground state is rigid, because you may have other action ground states different than this original one, but then they will all have the same energy, the same mass, and of course, as a consequence, the same energy. Okay.
Sorry, so just to may I just define this? So you're saying that if there are energy ground states, then the problems are equivalent for that or not?
Okay, in some sense, let's say this: if you have energy ground state, you know a lot on action ground states. Okay, but be careful. I have an energy ground state at a mass mu. Okay.
No, for that mass.
Let's say better than this mass for that frequency, in the sense that you get an energy ground state. That energy ground state will have a frequency.
Okay.
Then at that frequency, you know everything, say almost everything. Okay. Of course, there is a problem, and here this is an important thing. I'm not saying that there is a perfect one-to-one correspondence between mass and frequency. Okay, and actually this is false. Okay, at least in full generality. Let's see why. Okay, so thank you for the question, because it allows me to move to the second part, which is, as Ugo was saying, I'm not saying that the problem are equivalent, but I'm saying something. Both this theorem and the previous one are somewhat telling you that you got a strong information that moves in one direction, in the sense that if you know something about the energy ground states, this implies a lot about action ground states. You move from energy to action, okay, in some sense. Now, it is natural to wonder if you can do the opposite. So can we reverse these two results? That is, for instance, as for this one, are action ground state also energy ground state? We don't know. But also the previous one, we know that minus E is the transform of J. Is it true that J is also the transform of minus E? That is this, sorry, say red equality here. Note that, again, this is not a silly question, because if this were true, you immediately have, by standard property of Legendre transform, that J is a convex function. Because the double transform of J, which is by our previous theorem, is equal to the transform of minus E. The double transform of J is just the convex envelope of J. And the function is convex if it coincides with is convex. Okay, so this is somewhat to ask about the convexity of J. Now, the answer to this question is, in full generality, no. Okay, and here is where the reversion, where the, say, symmetry between the two problems, the equivalence is lost. In particular, you immediately see that the answer to this question now depends strongly on the finiteness of the energy. If you look at the supercritical case, which is the case where the energy is always minus infinity, of course, except for the mass equal to 0, because in the zero mass constrained space, you always have the zero function. And in that situation, the energy is always 0. So this tells you that if you compute the transform of minus E, this is always a 0 for every value of lambda. So J star star is constantly equal to 0. But we already know, if you remember, if you recall the original properties of J that I was listing at the beginning, we already know that J is not always 0. There are frequencies for which J is strictly positive. So J and J star star do not coincide. J is not convex. And this is not surprising, because in the L2 supercritical regime, if you look, for instance, at J on Rn, you find a concave function, not a convex one. Okay? So even on Rn, you immediately see that this thing here is false. Okay, at this point, you may be tempted to say, well, okay, but this is the L2 supercritical case where ground states, energy ground states never exist, where the energy is always minus infinity and so on. Maybe this is a bad situation. Maybe if you restrict your attention to L2 subcritical or L2 critical powers where you do have a finite energy, you recover the relation you're looking at. No. In general, even when you got L2 supercritical power, you do not expect J to be always convex, okay? In particular, we got the following result, which tells you that, okay, here there is this assumption. Let me just skip it for the moment. I will comment it in a bit. Suppose you have a frequency, lambda bar, at which there are two action ground states with different masses. Then at that frequency, calligraphy J is extremely larger than its convex envelope, and in particular, it is not a convex function. Now, let me say immediately that the finite measure assumption on omega is again not restrictive in the sense that it can be relaxed. It is there just because we want to find, say, a framework where to easily state this result. And the finite measure, it helps in ensuring existence of ground states, both action and energy ones, for every value of lambda and mu. Okay, you can drop it, but and you can extend our result to, say, infinite measure domain. In that situation, you need to develop an analysis of the existence of ground states independently. Okay, but that can be done. It can be done in a lot of different situations. Okay. The point here is that this theorem is somewhat revealing an asymmetry between the action problem and the energy problem. Let me state it like this. Before, we've been seeing that whenever you have one energy ground state, then at the corresponding frequency, the action problem is extremely rigid. All ground states of the action share the same mass. Now, we are saying that if I'm able to find two action ground states with different masses but same frequency, then there will be at that frequency no energy ground state for any value of the mass. Of course, because if at that frequency there exists for some mass an energy ground state, well then by our original result, all action ground state at that mass, at that frequency will have the same mass. And this is not possible because we are assuming that we already have two action ground states with different masses at the same frequency. Okay, so you see, in some sense, there is this asymmetry. If you have a situation like this, if J is not a convex function, then you expect to find, if you look at the frequency of the energy ground state as a function of the mass, you expect to find not, say, a continuous function, but a function with a jump. Okay, there are some frequencies that do not correspond to any energy ground state for any value of the mass. Okay, there you will find a non-convexity of your function J. Okay, so this is, say, the first major part of the talk. Let me say that, let me move to the final one. Note that since we do not expect J to be convex, we got problem also at the level of differentiability of J. Because as I was saying before, we know that the energy E is concave. And this immediately gives you right and left derivatives everywhere. This result can be improved. We can also characterize the derivative of the energy. This was done in a previous paper, still in collaboration with Serra and Tilly. The original paper was on metric graphs, but the part about the differentiability is completely general. Okay, so it is the very same kind of proof, the very same argument, also on open subsets over n. Out of the technicalities of the result, the key point is that the energy, the ground state energy level, is differentiable out of at most countably many masses. And when it is differentiable, the derivative is equal to minus the frequency of the energy ground state at that mass. Okay, so out of at most countably many masses, the frequency of the ground state depends only on the mass, and it gives you the derivative of the energy. The question now is, what can we say about J? Because J is not convex. So we do not even know that it is differentiable everywhere or almost everywhere. The result is J still is differentiable. We need to perform another strategy to end up with this result. This strategy requires some assumption. You can see here example of assumptions that are sufficient. They are not necessary. They can be relaxed. Okay. Let me just say that the spirit of this assumption is the same of the assumptions you need to obtain the previous result about the differentiability of the energy. Okay, so essentially the take-home message is, for the differentiability of J, even though you do not have the convexity, you do not need stronger assumptions than the one you need for the differentiability of the energy. Okay, they are essentially quite of the same. Of course, translated in the notion in the context of the action. The thing we can say is that again out of technicalities, the action ground state level is always differentiable out of an at most countable set. So for all but at most countably many frequency, the mass of the action ground state only depends on the frequency, and the mass is exactly the derivative of J. Okay, the same result except for the minus here that we already saw in the previous slide about the energy. Okay, so this is almost everything I wanted to say about ground states, global minimizer. Let me conclude where, say, two further observations. The first one, okay, sorry, I was forgetting about this. Let me just say that maybe someone in the audience here, when looking at this result of differentiability, is thinking of well-known results on instability theory. There are some results essentially if you think of the stability theory by Grillakis, Chatin, and Strauss, you may say, well, okay, but this is essentially the same thing. Of course, the final result is the same, but be very careful. In the stability theory, the zero level assumption to end up with the differentiability result is, let's take a C1 curve of solution. In general, you do not know that ground states, for instance, action ground states, you do not know in general that they are a C1 curve parameterized by the frequency, okay? So you cannot have this assumption in full generality, and all these results recover the expected differentiability property of J and D, getting rid of the regularity assumption on the curve of solution, okay? There is no regularity assumption on the curve of the ground states here. Okay, so as I was saying, the final results I'd like to show to you. First one, the local counterpart. Some slides ago, I said there are a lot of interesting questions about the relation between ground states, but we can also wonder if there is a relation at the level of local minimizers. There is a relation. Essentially, the relation goes in the same direction we've already seen for global minimizers. We got this result that tells us that if you have a non-degenerate local minimum point for the energy in the mass constraint space, then this is also a non-degenerate local minimum point of the action in the Niari manifold. So again, energy implies action in some sense. About this result, we can say that this is always true for every power between 2 and 2 star. This is essentially based on a comparison between the second derivative of the two functionals. So as long as you can perform the explicit calculation, everything is fine, the result works, and there is no role of the L2 critical power here, okay? The calculation can be performed up to P equal to 2 star. Again, note that this result is in general sharp, because one cannot expect local minimum of the action, not even global minimum of the action in the Niari manifold, to be also local minimum of the energy. We have a counterexample that is the soliton on Rn in the L2 supercritical case. In that situation, as I already said, they are action ground states, but one can prove that they are orbitally unstable. And since, on the contrary, and this is a general result by, say, Cazenave-Lyons in 1982, local minimum of the energy in the mass constraint space are always stable solution, this is immediately telling you that the solitons in the L2 supercritical case in Rn are not energy ground states. They are not even local minimum of the energy in the mass constraint space, okay? And as I was saying before, this is the same reason, there's the same thing that happened in the L2 supercritical case, also if omega is the Born, okay? Again, by the paper by Norris, Tavares, Verzini, and Fukuizumi at collaborators that I already quoted before. Okay, so definitely ending my time. Let me just conclude with the very last slides, which is, say, in some sense about perspectives, in a very broad sense. Well, let me say this thing first. All the results that we've been seeing, except possibly for the differentiability of J, I said possibly just because the proof we have for the differentiability of J, the one we have, doesn't work straightforwardly in the case of combined nonlinearities. But this is not telling you that J is not differentiable in this case. I believe that J is differentiable. I even believe that maybe a suitable arrangement of our proof should work, but we do not have that arrangement at the moment. So forget for a moment of the differentiability of J. All other results remain true, even in the case of the model with the double nonlinearity, these combined nonlinearities, which has been largely studied in the last, I don't know, let's say the last 10 years by many authors. There is an interesting thing. It is important for our result to extend that both nonlinearities have this sign. both of them have a plus sign on this side of the equality. Let me say why. Well, first thing, before talking about combined nonlinearities, let me just say that, sorry again, it wasn't my fault. Okay, the thing I was saying, I was just concluding with final remarks about, say, similar question similar questions that have been recently addressed by other people, in the sense that when we started thinking about this problem with Enrico and Paolo, say we were a bit worried at the beginning, in the sense that this question seemed to us too natural to not have been already solved by some. Okay, so okay, we finished our preprint, we put it on the archive, and then at least I speak for myself, there was a first period where we were always, I don't know, worried that, I don't know, maybe at some point we were receiving an email, but someone saying, oh, very interesting result, but unfortunately, these are all well-known things by the 80s, just take this standard book, okay? Because it seemed to us that the relation between two well-established different approaches should have already been addressed before, okay? Now, actually, we received an email 2 weeks later at the end of our preprint, but it wasn't an email of a different taste, in the sense that it confirmed us that actually the problem weren't studied, haven't been studied before, and for some other people were also interesting. We received an email by Jean, which say 2 weeks after we completed our preprint, posted on the archive a preprint of his in collaboration with Lou, where they somewhat tackled a similar problem. They restricted their attention to only to the case of Rn. Okay, and Rn is very important in their proof, because they're exploiting the invariance by dilation, okay, and the possibility to rescale the function. But they were able to prove that energy ground states are also least action solution. So kind of the same result we have before. Be careful that they talk of least action solution, because the difference between their paper and ours is not only that they're dealing with Rn, but it's also the fact that they can deal with more general nonlinearities, not only with the pure power nonlinearity case. And of course, if you deal with the general nonlinearity, you do not always have an ERE manifold. Okay, so in some other situation, for some nonlinearity, it doesn't make sense to look for the minimizer of the action on the ERE manifold. When the ERE manifold is not available, you simply look for the solution, say the critical point of the action with the least possible value of the action. Okay, and that is the least action solution. But they were able to prove that even in this more general setting, energy ground states, provided they exist, are least action solution. There are also, and with this I conclude, other recent papers which are not directly related to our question. It is a couple of papers. There are a couple of papers, say one by Karl, Klein, and Sparber, and another one by Mathieu Lewin and Rotanodari. They actually focuses on existence of solution for this model, which is, you see again, a model with combined nonlinearities, but be careful now, the largest nonlinearity has a negative sign. So this doesn't fall in the case for combined nonlinearities we are able to cover. Actually, in this situation, you do not have the ERE manifold. At least say it's not available as a natural constraint. Okay. In this situation, the thing I'd like to say is that when you look at the problem in R3, in R2 this is not the case, but in R3 they are able to show the existence of least action solutions that are not local minimizer of the energy. And this is not surprising, because it is more or less like the soliton for our problem in the L2 supercritical case. But in this situation, this happens even in a regime where energy ground state for large masses do exist. So this is different with respect to Rn, to our problem. In our problem, in the L2 supercritical case, in Rn, the soliton is an action ground state. it is not a local minimizer of the energy because there is no local minimizer of the energy at any mass. For this problem, the fact that you're dealing with different solution, if you look at the action approach or the energy approach, remains, but you still have solution in the energy approach. Okay, so maybe here is something different. I mean, this is just a point I was finding interesting in these two papers that may have some relation with the thing we've been discussing today. This is definitely the end. So let me just skip to the final slide and thank you for the attention. And again, sorry for the inconvenience.
Thank you very much.